Hello everyone, here's a video on the gas laws. Okay, so there's about 3 or 4 gas laws that we'll discuss today in this video. So the first one is Boyle's law, and to discuss the gas laws, I suppose first as a whole, we're going to look at how pressure, volume, and temperature all affect each other. Okay, typically we'll look at how pressure and temperature affect the volume of a gas. Remember, a gas can actually move a whole lot because the particles slide past one another, and second of all, the particles can be squeezed or expanded because the spaces between those particles are quite large. Okay, so Boyle's law, let's take a look at that. Boyle's law basically says that if you push on a gas in a closed system, and here we go, here's a syringe. So if I have a syringe here, and here's the end of the syringe, and I push on the syringe here, and I squeeze the gas down, I push on the gas, it can squeeze the gas down so the volume will decrease. So an increase in pressure leads to a decrease in volume. And the reason why this happens is because, again, there are tremendously large spaces between particles between the gases. So, between the gas particles. So therefore, those particles can be minimized or squeezed in order to diminish that volume, or the result is the diminishing of the volume. Here's the equation that we're going to use, where the 1's and 2's you're going to see are all initial conditions and final conditions, okay? So as long as you keep them together contextually, it should work out nicely. So just doing one problem here, if I read the question, it says a gas at 1.34 atmospheres and 1.8 liters is subjected to a higher pressure of 2.00 atmospheres. What's the new volume? Well, again, contextually, it appears as though these two go together. So I'll call that my, this one's my P1, and this one's my V1, okay? So let's use our equation of P1, V1 is equal to P2, V2. And I want to solve for V2, because it says, what is the new volume? So that's my X, okay? This is, by the way, my P2. All right, so it appears as though my pressure is increasing, so that should diminish or decrease my total volume. My answer should be less than 1.8 liters, in other words. You're going to find that in class I like to get X alone, and since X is V2, I'm just going to divide out by P2 on both sides, thus crossing that off, and I end up with P1 V1 over P2. So I'm going to plug into this equation here, okay? So if I have V2, if I'm looking for V2, let me plug in the P1, and the P1 is 1.34 ATM, and the V1 is 1.8 liters. Okay, so that's my initial pressure, my initial volume, and I'm going to subject that to a greater volume of P2, which is 2.00 atmospheres, and the atmospheres cancel mathematically, and I end up with, I believe, 1.2 liters. So it did go down. Okay, the answer to this is 1.2, and the volume decreased because the pressure increased. Okay, so solving for X, these are actually quite simple. Let's move on to Charles' law. Charles' law is a little bit more complex in how it came about, so let me discuss that very quickly. So two things came about from his experiment. It was absolute zero was a concept that was somehow came about, and then the Kelvin scale is also something that we'll talk about here too. So you'll notice that there's a temperature scale here, and what Charles did is he took 1 liter of a gas, and the gas was in a piston, so the piston can expand or contract. Okay, it's all pistons like a syringe. Okay. The 1 liter of gas, as he heated it up, he found that when he hit 273, the volume doubled. So he had 2 liters of total gas. Okay? So you'll notice as the volume doubles, it's because the temperature is increasing. The particles are moving faster. We'll talk about this later as the kinetic molecular theory. But as the particles are moving faster, they want to expand out. So as it moves out, pressure stays constant. So pressure won't be an issue here with Charles' law. Pressure we won't even talk about because it stays constant. So the volume increases as it got hotter. So he did the same thing, but except in the colder range. But he could only get it so cold, and so he says, well, if at 273 the volume doubles, then at negative 273 the volume must diminish down to nothing, and we should have no volume whatsoever. And this is a theoretical point. This is a theoretical temperature. We've never got down to negative 273 degrees Celsius. We've gotten very close with special instruments, but we've never gotten this cold. So absolute zero is a point, which is a temperature at which all matter stops and the volume of a gas is zero. Now, it takes up no space at all. Okay. Now, here's the problem with absolute zero. There's not zero. It's actually no negative 273. So this is where the Kelvin scale comes in. The Kelvin scale says that absolute zero is 0 Kelvin. That's the same as negative 273. Okay. So if I'm going to add 273 to get to 0 Kelvin, that means I have to add 273 everywhere else. So 0 degrees Celsius is actually 273 Kelvin, and this is all the way 273 times 2, whatever that is. But room temperature typically is 25 degrees Celsius, and that converts to 298 Kelvin. Okay, so in order for us to deal with the Kelvin scale, and all gas laws must deal with the Kelvin scale. The reason why we deal with the Kelvin scale is because the Celsius scale has the negatives, and the negatives play with our calculations. So we need that Kelvin scale where every temperature is 0 and up, okay, or not negative. So this is what you do. And whenever you're converting to Kelvin, we are going to add 273. Okay, so all calculations must be done now in Kelvin when we talk about temperature. Okay, so we already discussed the relationship of Charles' law, and it basically says as temperature increases, the volume also increases. The reason is the particles are moving more. As they move more, they collide more with themselves and the sides of the container. And if we have a flexible container like a balloon or a movable piston, the pressure is alleviated because the volume keeps expanding. So what's the relationship? As temperature increases, particles move more, and the volume increases. Okay, so this ends up being a relationship where we have volume over temperature. Now don't forget, we also have this thing called STP. STP is standard temperature and pressure. You'll notice I'm not going to spend a whole lot of time on this. Standard temperature is 0 degrees Celsius or 273 Kelvin, and the standard atmospheric pressure could be any one of those 5 or 6 that you're responsible for knowing. Okay, so that's STP. Whenever you see STP, you see two numbers. You see a temperature number and a pressure number. Okay, so standard temperature and standard pressure, they simplify that by calling it STP, or standard temperature and pressure. Okay, one problem with Charles' law. Let's do a problem with Charles' law. So it says a gas occupies a 900 milliliters at a temperature of 27 degrees Celsius. What's the new volume at 132 degrees Celsius? So we have these two go together. Okay, so 900 milliliters is our V1. 27 degrees Celsius is our T2. But it's not 27 degrees Celsius, it's actually 300 Kelvin. Okay, that's what we'll use. And at a temperature of 27, what's the volume? So V2 is our X, and our T2 is 132. Now I have to add that up. I can't quite do that in my head in a moment's notice. So that's 405 Kelvin. Okay, so there's all our numbers. Let's plug into an equation. So the equation that we're going to use now is V1 over T1 is equal to V2 over T2. And we're asking to solve for V2. So let's get our T2 up here by multiplying it on both sides. And we end up with this. Okay, so let's plug into that. Our T2 is 405 K. Our V1 is 900 milliliters. And our T1 is 300 K. K's cancel mathematically, so let me just calculate that very quickly. That's 405 times 900. Whoopsie. 405 times 900 gives us a large number, divided by 300 gives us an answer of 1,215 milliliters. And I guess we need to ask ourselves, does that make sense? Well, temperature increased, and we know Charles' law says that anytime you increase the temperature of a gas, it will increase its volume. So yes, that works. That's a good answer. Okay, moving on to, here's another problem. Let's go to Avogadro's hypothesis. Very quickly, Avogadro basically said that the volume of a gas at a constant temperature and pressure is directly proportional to the number of moles of a gas. So if I have two equal volumes of gases at the same temperature and pressure, they contain equal numbers of particles. So if I have this volume of gas here and this volume of gas here, okay, and they're at the same T and P, so the temperature and pressure are exactly the same between them, they have the exact same number of moles, where N represents moles and N is exactly the same. okay? So N is exactly the same, or again, the number of moles. That means that if I have double, well, I'll get to that later. Okay, we're getting a little bit ahead of ourselves. So with Avogadro's hypothesis, we have Avogadro's law. And basically it says that a volume of a gas and the number of particles are directly proportional. You increase N, which is the moles of the gas, or the particles of the gas, you increase the volume. That's as simply as saying is that I can take a balloon and blow it up and tie it off, and I could untie it and blow it up more, and it just gets bigger, okay? So more moles equals a greater volume, okay? And you can work through these problems on your own. They are on the website. Let's get to the combined gas law, which actually just says all three are in play now. PV over T. And actually, from what I have been teaching in the past, if you just remember PV over T, you can work with all the gas laws no matter what combination you get, okay? PV over T, PV over T. So if you notice how it works here, if you have pressure and volume mentioned in a problem and temperature stays constant or temperature is not listed, now you have Boyle's law, okay? So just cross that out. Again, if you memorize PV over T and you have pressure stays constant or it's not mentioned in the problem, now you have Charles' law, which is V over T. You don't need to know the names associated with the actual gas law. You just need to explain the gas law. If you have pressure over temperature and volume is not listed, you have something called Gay-Lussac's law, which is different than the Gay-Lussac's law we just talked about, okay? If you have all three mentioned, then you have to use all three. Okay, and again, that's solving for x. Okay, so going through, I'm not going to do any problems, and then the next video, of course, will be the ideal gas law. But anyway, check out that stuff. I'm going to sign off from here.